So it's time for Fun with Math, and today we're going to do the review for Exam 1 on techniques of integration. So the review here, you're supposed to complete the following tasks. So the first thing you want to talk about are make sure that you guys review the basic types of integrals. So let me go through this real quickly with you. So what are the basic types of integrals? Well, the idea is you should be able to integrate a nice easy power of x. So the integral of x cubed dx, which is just x to the fourth. You add 1 to the power and you divide by it. And don't forget plus c. Oh, and even before that, you should be able to integrate a constant, like the integral of 7 dx. And so that would just be equal to the constant times x plus c. Remember what this is actually asking you for. When you see this integral in dx, it's just basically asking you for the anti-derivative. So if you take a derivative of this thing, the 4 comes down, knocks off the 4 on the bottom, you get x cubed plus the derivative of constant 0. You get back the thing on the inside here called the integrand. So you can always kind of guess. Well, that's not right. You can always just sort of guess and check. All right, so what other basic types of integrals should you know? So you should also know the integral of e to the x dx, and also the integral of 1 over x dx. And so this is equal to the integral of e to the x dx is just e to the x plus c, because the derivative of e to the x is e to the x. And this one's equal to the ln of absolute value of x plus c, because the derivative of ln of absolute value of x is 1 over x. And then we have some of the trigonometric expressions you should be familiar with. So you should be able to integrate the sine of x. You should be able to integrate the cosine of x. You should be able to integrate the secant squared x dx. And then you should also be able to integrate secant x tan x. So these are the 4 types that I'm very familiar with. So if you integrate sine of x dx, my guess is cosine of x plus c, but you would be off by a negative sign, because when you take the derivative of cosine of x, it's negative sine of x. You put a negative right there. The integral of cosine of x, my guess would be sine of x, and then plus c. And if you take the derivative of sine of x, you get back cosine of x, so it's good. The integral of secant squared x dx is tan x plus c. And that's because the derivative of tan of x is secant squared x. And then over here, the integral of secant x tan x dx is just a secant x plus c. So if I know all 4 of these types, I basically get my other types for free. So like if you want to integrate the cosecant squared of x dx, if for some reason that pops up, I know it kind of mirrors this type of formula. So my guess instead of tan of x would be cotan of x plus c. And of course I'd be off by a negative sign. And the same thing goes for the integral of cosecant x cotan of x. It's another one of my types, but I don't really bother to memorize it, because if I know this one, I get this one for free. It's cosecant of x plus c. And of course I have to remember that negative sign right there, because you take the derivative of cosecant of x, it's negative cosecant x cotan x. So you put a negative and those 2 negatives will cancel. And there's one last type you should be familiar with, because it does come up quite often. 1 divided by 1 plus x squared dx. And that's equal to tan inverse of x plus c. And so these are my basic sort of types of integrals that I need to be familiar with in order to integrate more complicated integrals. All right, let's go back up to where we were before. And so those were the basic types of integrals. And then next we have to do the sort of trigonometric identities. So we want to make sure we're familiar with some basic trigonometric identities. So let's look at what these are. So you have quite a few of these. So you have what are called the reciprocal identities. And these are not even things that I feel like I should have to tell you you need to memorize, because you should know this forwards and backwards. And if you don't, make some flashcards. So here, you know, the reciprocal identities are like, what is a secant x equal to? or the cosecant x equal to, or the cotan of x equal to, in terms of sines, cosines, and tans. So this is equal to, it's always 1 over opposite the letters, so it's 1 over cosine of x. This is equal to 1 over sine of x. And of course this is equal to 1 over tan of x. These are very important because if you're going to evaluate like the secant of pi over 3, I have no idea what the secant of pi over 3 is unless I convert it to cosines. And so it's 1 over the cosine of pi over 3. And then I have to think about what the cosine of pi over 3 is. And so in my head, remember I have this table. You have 0 degrees, 30 degrees, 45 degrees. Oops, I'm writing 45. 45 degrees, which is pi over 4. 60 degrees, which is pi over 3. And 90 degrees, which is pi over 2. And so this is my angle theta. And remember, I know the sine of theta and the cosine of theta. And so this table kind of lives in my head. I remember the sine of 0 is 0, so this is square root 0, square root 1, square root 2, square root 3, square root 4, and then these are all divided by 2. It's a 1 there. These are all divided by 2, and these are all divided by 2. These are all divided by 2. And the cosine of theta is exactly the same. You just write it the other way. So square root 4, square root 3, square root 2, square root 1, square root 0. And these then are all divided by 2's also. And so if you ask for the secant of pi over 3, my brain will have to go up here and say, okay, well, it's 1 over the cosine of pi over 3. Well, here's pi over 3. Oh, that's 1/2. So it's really 1 divided by 1 over 2. If I multiply by a reciprocal, that's the number 2. So that's what the secant of pi over 3 actually is. All right, there's also the quotient identities. So I'll just write quotient here. So quotient identities, that tells me what the tan of an angle is and what the cotan of an angle is in terms of sines and cosines. So these are very important. This one's sine of theta over cosine of theta, because oftentimes we're going to convert everything to sines and cosines and then try to use their identities to simplify expressions. And then the cotan of theta is equal to the cosine of theta over the sine of theta. Okay, so those are sort of the very most basic identities. And then of course you build in a little bit and you have the Pythagorean identities. Right? So the Pythagorean identities here versus the quotient identities. And so this comes from the fact that the way that the cosine and sine function are defined is they're defined on that unit circle there. So remember, on the unit circle, the way that we sort of define the cosine and sine is you have this unit circle that has radius 1, so -1, -1, and 1. If you take any point on that unit circle, like a point right here, it's going to have an input value and an output value. The input value is going to be the cosine of theta, and the output value is going to be the sine of theta, where theta is this angle right here. So that's theta. You can also think about this as the cosine of theta being, the input, so it's the length right here of this right triangle. And of course the sine of theta is the output, so you make a little right triangle here. So that's the sine of theta right there, and we'll turn the hypotenuse blue. The hypotenuse here has length 1 because it's the radius of the circle. But that's the idea. But this is a right triangle, so we know that x squared plus y squared is equal to 1, or if you like, cosine squared theta plus sine squared theta is equal to 1. So that's called the Pythagorean identity, because you use the Pythagorean theorem to create it. So cosine squared theta plus sine squared theta is equal to 1. Now from this you get the other two identities. So if you divide out everything by cosine squared theta, this will turn into a 1. This will turn into a tan squared theta. And if you divide 1 by cosine squared theta, you get a secant squared theta. Then instead of dividing by cosine squared theta here, you divide by sine squared theta. You get cotan squared theta plus a 1 is equal to 1 over sine squared theta, which is a cosecant squared theta. So those are the Pythagorean identities. So I'm going to skip the double angle identities, but we have these. I'm going to come back to these. So the double angle. Oh, I guess we can do them. We'll do these. So double angle identities. So these come up from just time to time, and so that tells you how to reduce a double angle if you ever need to. So like the sine of 2 theta, that's actually equal to 2 times sine of theta. cosine of theta. And then the cosine of 2 theta is the one I always have a hard time remembering. But it's easy if you think about it in terms of instead of a plus, you just put a minus there. So it goes cosine squared theta minus a sine squared theta. And there's two other versions of this identity. So you have two other things that it's equal to. And the way you find these two other things is you simply plug in, oh, that's a square. You simply plug in for sine squared theta right here. So, you know, this sine squared theta you can solve for, and then it's 1 minus cosine squared theta. And so what you're going to get is then 2 cosine squared theta minus 1 when you plug in for this. And then if instead of plugging in for this, you plug in for that, you use this identity, solve this here for cosine squared theta, you'll get 1 minus 2 sine squared theta. And then from these, you can get the power reducing identities, which come in really handy. These come in really handy when you're trying to do like something like the integral of cosine squared theta d theta. And so these basically reduce that cosine squared theta to a single cosine of double the angle. So this one's 1 plus cosine of 2 theta, all divided by 2. Whereas this one down here, if you do sine squared theta, instead of plus, you just write minus. So it's 1 minus cosine of 2 theta divided by 2. And sometimes I use these actually right here to develop these down here, because I can solve this for cosine 2 theta and I get this formula right here. I can solve this for cosine 2 theta and get that formula down there. But these are the basic sort of trig identities you should be somewhat familiar with. Okay, let's go back up. So we have reviewed the sort of basic type of integrals and trig integrals. And you want to make sure you review this homework on integral tables and numerical integration. We didn't have time to go over the homework in class, so I posted the solutions online. Like I say here, one problem on the exam will be on numerical integration. So make sure you can use those 3 formulas, the midpoint rule, trapezoidal rule, and Simpson's rule, to approximate definite integrals. Okay, so let's go down here and let's kind of determine the technique of integration that can be used to find each integral. We'll write an S for substitution, an IP for integration by parts, a TI for trig integral, a TS for trig substitution, and a P for partial fractions. So there are some strategies when you want to integrate, like for a trig integral. That's actually pretty easy. You're just looking for an integral that just involves a trigonometric expression. So like this one here, this would definitely be a trig integral. Right. Over here, you could argue this one actually could be a trig integral if you really wanted it to be, because, you know, really remember what this actually is. This is the integral of secant squared of 3x dx, because it's 1 over cosine squared of 3x. So you could argue that this is a trig integral, but this is certainly a trig integral. The way you would integrate this is you have to use an identity to get rid of the tan squared x, and which we'll actually look at in a little bit. All right, so that's one strategy. Look for trigonometric expressions. Partial fractions actually is usually pretty simple too, because you're just looking for a polynomial divided by a polynomial. So I would guess that this is probably going to be by partial fractions. And trig substitution is actually usually pretty nice too, because it usually involves the square root of something squared plus or minus something else squared. So like down here, this is trig substitution for sure, because you have the square root of x squared plus 9 on the bottom. And then we're kind of left with the ones that are a little bit tricky sometimes, substitution and integration by parts. So substitution, you need to see a function typically, right? So here's substitution. You see a function and its derivative. So over here, this is probably substitution, because on the bottom, I can let this be the function, and its derivative is basically e to 3x, right? The derivative of this down here is 2 e to 3x times the derivative of the inside, which is 3, and then minus 0. So basically, the derivative of the bottom is 6 e to 3x. So the idea is like, oh, I have e to 3x on top. So if I have the function on the bottom, if I let u be equal to the function on the bottom, I'm going to get du basically to be something that I have on on top. And we'll do that in a little bit, but that's why this one is substitution. Whereas this one, I see two functions, but I don't see their derivatives anywhere, so I would guess this one's probably integration by parts. And even though that this is a trig integral, this trig integral can also be done, if you want, slash by substitution, because this is basically one of my types. So if you let u be equal to 3x, you can turn this basically into one of your types. So you could argue that this is a trig integral or it's substitution, or you could say it's kind of both. It's a trig integral with substitution. All right, so now what I want to do is I want to move on and actually do these integrals. And so let's take a look at the first one here. And so the first one, we already kind of started out, so let's write it as a secant. So we have this as secant squared of 3x. All right, that shows me it's basically one of my types, but the problem is you have 3x in there. So what I'll do is a substitution to kind of simplify this. So u is equal to 3x. And you could guess and check here, but I'll do a substitution on it for fun. And the derivative of 3x is 3, or the dx over here. And then the idea is you're just going to plug in. So this is going to be equal to the integral of secant squared, and then of 3x, but I'm going to write a u there. And then dx, well, dx is actually du divided by 3. So I'm going to move that 3 over so I can get my dx by itself. And so I'll plug in for dx du divided by 3. And so that's equal to, I'm going to clean this up. I'll pull that 1/3 out. So 1/3 the integral of secant squared u. We really don't need parentheses, so let's write u du. And now this, remember, is one of my types. And so if you know that type, this is pretty simple. It's just 1/3, and this would be the tan of u, because the derivative of tan of u is secant squared of u, and then all plus c. And then don't forget to plug back in. Your u is 3x, so down here we'll have 1/3 tan, and where I see a u, I'll put a 3x, so of 3x, and then all plus c, and that's my answer. So that's kind of like a trig integral with a substitution attached to it. Or you could say it's kind of like one of your basic types in a way. This one is definitely substitution. So to do this, the idea is I'm going to let my u be the bottom piece right here. So this is like u substitution. So u is going to equal my 2 e to the 3x, and then take off 7 on the end. When I take a derivative of this, I have 2 times a function. So the derivative of 2 times a function, the 2 stays, and you multiply it by the derivative of the function. So the derivative of e is just e again, so e to 3x. And don't forget, this is a chain rule because you have basically e on the outside and 3x on the inside. So derivative of the inside, derivative of 3x, is just the number 3. And then you're going to take off 0, and then multiply all that stuff by dx, right? Derivative of 7 is 0. So what do we have here? We have du is equal to, and we have 2 times 3, which is 6. Oh, I made a mistake here. That's not 3x. That's just the number 3, right? The derivative of 3x is just the number 3. So let's clean that up or fix that. So that's just a 3 right here. So hopefully you caught that mistake. If not, change it. And so down here, I have 6 e to the 3x dx. And I'm about ready to make my substitution. I might clean this up just a little bit so it's really clear what I'm doing. So I can write this as 1 over e, 2 times e to the 3x minus 7. And I can write that e to the 3x on the outside here times dx. And notice I can divide both sides out by my 6. So du divided by 6 is equal to this e to the 3x dx. And then I have it. So on this thing here, that's my u. So the idea is if you just flip that over on the other side, I have the integral of 1 over u. And then this is really my du divided by 6. So if I flip that over, right, flip this over, on the other side, you really have du divided by 6. And I can clean it up a little bit more, pull out that 1/6, and the integral of 1 over u du. And so finally, that's one of my types. And so I can integrate that. So that's equal to 1/6 ln of absolute value of u plus c. All right, so notice, this is one of my types. So the idea is you just flip this shape over, and on the other side you have the actual formula there, and you're just replacing it. And I got to substitute back in for u, so I get 1/6 ln absolute value of 2 e to the 3x minus 7 I'm just plugging back in for my u. That's what my u is. And then all plus c. And that's my answer. And so if you took a derivative of this, hopefully you would get this back, because that's what it's supposed to be. All right, so that was a good substitution problem. Let's look at the next one. All right, so now this one was integration by partial fractions. So the idea on this one is that we can rewrite this. Let's factor the bottom. So that's x minus 2 on top. And on bottom, we should be able to factor this, hopefully. So it's going to be x plus or minus something, x plus or minus something. We have a dx here. The somethings come from the 8, so I'm thinking 2 and 4 probably. So let's check 2 and 4. So we have to take 2 and 4, add or subtract them, and get 6. And I can do that. That's a plus, and that's a plus. And so what integration by partial fraction says is that this thing has a partial fraction decomposition. So it can be rewritten as a divided by x plus 2 plus b divided by x plus 4. And so if we can figure out what a and b are, then we can integrate these terms with respect to x and get our answer. And so this is equal to this over here. So we need to find a and b, so we simply set them equal to each other and solve. So x minus 2 divided by x plus 2, x plus 4. And we set that equal to this partial fraction sort of decomposition. So here's a partial fraction. We're just decomposing it in terms of these two partial fractions. And to solve for a and b, it's actually pretty simple. This is a rational equation, so to solve for a and b, we'll clear the denominators by multiplying both sides by x plus 2 and x plus 4. When we do that, on the left-hand side, the denominator clears, and you just get x minus 2. On the right-hand side, this x plus 2 is going to clear with this x plus 2, but it's going to leave you with an a times x plus 4 on top. And then plus b, and so now when you multiply this here, the b is going to stay, but the x plus 4s are going to clear, and you get x plus 2. And so what we have now is something without denominators, so we have cleared the denominators. And to find a and b, there are a couple ways to do this. One way is you can multiply all this out and do something called equating the coefficients. So whatever the x number on the x terms are, they have to be the same, and then the constants on both sides need to be the same. But the easier way to do this is just plug in numbers that make things go away. So like if you plug in negative 2 here, this whole term is going to go away. So let's try x equal negative 2. On the left you get minus 2, which is a negative 4. On the right you just have an a times negative 2 plus 4, which is just a 2. And of course plus 0, because this term is going to go away. Negative 2 plus 2 is 0. So that tells me that a has to be equal to, you divide both sides by 2 and get a equal to negative 2. So there's my a value. And to find my b value, I'm going to do exactly the same thing, but instead of plugging in negative 2, which made that 0, I'm going to plug in negative 4, which will make that equal to 0. So plug in negative 4. So negative 4 minus 2 is a negative 6. This term is going to go away because I'm plugging in negative 4 for x. And then over here, I'm going to get b times negative 2. And so this is going to imply, when you divide out by negative 2, that b is equal to 3. And so now I basically have it. This integral here is going to be equal to negative 2 over x plus 2, and then plus a b, my b is 3, over x plus 4 dx. And now these are basically like one of my types, so I can just kind of guess and check. So my guess is this is going to be negative 2 ln of x plus 2, an absolute value, plus 3 ln of absolute value of x plus 4, and then all plus c. And that actually checks. If you take a derivative of this, it's negative 2 times derivative of ln, which is 1 over x plus 2. Derivative of the inside is just a 1, so you get that back. And the same thing here when you take a derivative of this. You can leave it like this if you like. If you want to be a bit fancy, you could rewrite this as ln of, and then you'd have the absolute value of x plus 4, and you could cube it, because you can move that 3 up into a power, and then divide it by, because that's a minus, and then you could square this if you wanted to and drop off the absolute values because you're squaring it. So x plus 2 quantity squared, and then all plus c. But you really don't have to go from here to here. This is a great answer. So if you want to leave it like this, I think that's great. So just leave it like that. All right, let's look at number 4. Now, number 4 is a definite integral, so we do this basically like we do indefinite integrals, but then we have to plug in numbers at the end. So we kind of have to keep the numbers on here. It's a trig integral, and the idea is that we can't integrate a tan cubed theta, but what we could do is we could think of this as being tan squared of x times tan of x dx, and we could get rid of this tan squared of x with an identity. So we have this identity, 1 plus tan squared x is equal to secant squared x. Now, I'm not sure if this is going to do anything or not, but it's something that I can do, and so when I do that, we'll see what happens. So this is equal to secant squared x minus 1. And so we're going to plug this in for our tan squared of x, and so that's going to be equal to the integral from 0 to pi over 4 of, in parentheses, we have secant squared x minus 1 all times tan of x dx. And so then that's going to be equal to the integral from 0 to pi over 4 of, and we'll have secant squared x here, so secant squared x times the tan of x minus the tan of x dx. And so now I'm thinking, oh, well, this is something pretty good, because you know the derivative of tan x is actually secant squared x. So you have a function and its derivative, and then to integrate this tan of x, well, I can't integrate tan of x directly, so but maybe I can convert to sines and cosines and integrate it. So let's just see real fast so you can see what's going to happen here. So I'm going to rewrite this as, I'm going to write this as tan x first because that's the function. Then here's its derivative, secant squared x, and then minus, I'm going to write this as sines and cosines. Because then what do I see? I see something like I have a function on bottom and its derivative on top. So now if you want, I can actually probably guess and check to see how to integrate these. But if you weren't able to do that, you could actually do a u substitution by breaking these things up. Right? So here's my guess and check. I'm going to put my guess and check right down here. So I would probably guess that this is going to be a tan squared x divided by 2. That's probably this one, and that's because the 2's are going to come down and cancel of tan x times its derivative, which is secant squared x, minus, and I would guess that this is going to be an ln of absolute value of cosine of x. Now here I'd be off by a negative sign, because the derivative of ln is 1 over cosine times the derivative is negative sign, so negative would be a positive, so that's actually a plus. And then this is going from 0 to pi over 4. Now, if you don't see that, that's okay, because you could actually break this up into 2 separate integrals. So if I was struggling with this one, I might just break it up into 2 separate integrals and then make 2 different substitutions. So secant squared x dx, and then minus the integral from 0 to pi over 4 of sine of x divided by cosine of x. Cosine of x dx. So on this one, I probably would let u be equal to tan of x, and then du would be equal to secant squared x dx. And so you can see that I have sort of a direct substitution here. Whereas over here, I'd let u be equal to cosine of x, and then du equal to this derivative, so derivative cosine is negative sine of x dx. And in fact, this is also a direct, because I can put a plus here and move the minus inside here. And so if I do that, what am I going to get? I'm going to get the integral. This is going to be my u, and this is going to be my du. So I have basically just u du, and then plus, and then this one, I'm going to have my u on the bottom, and then my du on top. So then I have the integral of 1 over u du. Now I dropped off the limits of integration here because I didn't change my limits of integration. So if I want to do this correctly, I should probably change my limits. So here I have u of pi over 4, which is equal to tan of pi over 4. And so remember, that's a sine over cosine, evaluate pi over 4, and they have the same value, so that's a 1. And then I have u of 0, which is actually tan of 0. So tan of 0. And that's equal to tan of 0, remember it's sine over cosine, so it's like 0 over 1, so that's a 0. And so here my limits go from 0 to 1. And here my limits, I have a different u, right? So now I have u of pi over 4, which this one is equal to then cosine of pi over 4, which is equal to root 2 over 2. And then I have u of 0, different u than last time over here, so I'm using this u. And so that's cosine of 0, and that's equal to 1. And so this one is going from 1 to root 2 over 2. And so then I can integrate these, and I would get u squared over 2 from 0 to 1 plus ln absolute value of u from 1 to root 2 over 2. And so now you can pick it up wherever you like. We could evaluate this one here or evaluate this one down here. It really doesn't matter. So let's just keep this one going. I'm going to draw a little arrow here, even though I don't like to draw arrows, but I'll draw a little arrow. So I'm going to plug in a 1, and so I get 1 squared over 2. And then I'm going to plug in 0, and that's equal to a 0. And then plus, I'm going to plug in root 2 over 2, so I have ln of root 2 over 2. I'm going to keep that like that. And then minus when I plug in 1, so minus ln of 1. I had to drop off the absolute value because these numbers are positive. And so what's that equal to? Well, you have 1/2 here, and then plus ln of root 2 over 2. And that ln of 1 is equal to 0. And so that's my answer. If you went this route and you just sort of guessed and checked, you could do the same thing. So here you have tan squared of pi over 4, all divided by 2. And then plus, you plug in pi over 4 here, so ln of absolute value of cosine of pi over 4. And then minus when you plug in 0. Now when you plug in 0, this is going to be 0, and this is going to be ln of 1, which is also 0. So when you plug in 0, you basically get 0 here, 0 divided by 2, and then plus ln of 1. So that whole term is going to be 0 because ln of 1 is 0. And we're left with this over here. So tan of pi over 4 is 1. And if you square it, you get 1. So you have 1/2 plus the ln cosine of pi over 4 is root 2 over 2. Absolute values you can drop off because root 2 over 2 is positive. And you see you get exactly the same answer. Now remember, you can check this on your calculator. So if you have a calculator, you should probably take it out. Let me take out mine here, if I can get it to work. There it goes. All right, so here I can check this on my calculator. There are a couple ways I can do it. I can do it by graphing it, which I like to do because then I can see what it actually looks like. So I'm going to type this in, tan of x raised to the 3. You want to make sure you're in radians, so hit mode just to make sure you're in radians. See, right now I'm in degrees, so make sure you're in radians. All right, back to my y equals, so there's tan of x cubed. I'm going to make my window go from 0 to pi over 4. So I usually just put in the limits of integration here. Sometimes you may have to adjust this later if it doesn't round right. And then I go to zoom, and I do zoom fit. So I find 0. You can just hit 0, but I like zoom fit. It fits the output to the input you put in there. And so then when I zoom fit this, it should give me a decent looking graph. So there's my graph. And then what I can do is hit second trace and go down to number 7, which is the integral button. And it'll evaluate this definite integral. So my lower limit was 0. And my upper limit was pi over 4. So pi divided by 4. Hit enter. And I'll shade in the region that I'm computing and return this answer, 0.15342641. And it goes on forever and ever, right? That's just an approximation. So what I can do then is check. So down here I can type in 1 divided by 2 and then add ln of the square root of 2, kick it out, and divide by 2 in parentheses, hit enter, and you'll see that those two numbers are exactly the same. So now I know I did it right. So a calculator is a wonderful tool to check your work. Not to do your work, but to check your work. All right, so we're getting close to being done here. I think we have 2 more left. So let's finish off these 2. So now this one was integration by parts. And now when you do integration by parts, the idea is you kind of set it up the same way every time. I always like to put my u there and my dv there. And then once I know those two things, I can find v and du. So my u and dv are comprised of these things here. So I have to find 2 things, and it's really a guess and a check. So like if you tried to make this your dv, you'd be kind of stuck because you don't know how to integrate ln of x squared. So you really only have one choice. You're going to let your dv be your x dx because you can actually integrate that. And then you have to let u be ln of x quantity squared. And so I can integrate dv. It's pretty simple. So the integral is you simply add 1 and divide by it. So x squared divided by 2. You don't have to worry about the plus c here. And then you take the derivative of u. The 2 comes down, multiplied by the ln of x. And then times the derivative of the inside, which is 1 over x. And then you have your dx. All right, so now what? We can actually do this. So the formula is it's u times v minus the integral of v du. So we multiply these together. So you have x squared over 2 times an ln of x quantity squared minus this integral. So now when you multiply these together, the 2's are going to cancel, and so are one of the x's. So what you're going to get is just an x times ln of x dx back. And so that's nice. It's not one of your types, though. So what that means is you have to do integration by parts again. But that's not so bad. You're going to let u be equal to something and dv be equal to something. Then you can find v and you can find du. And so then the idea is sort of similar to before. If you let dv be ln of x, you can't integrate it. So what we let u be is ln of x. And then dv is the leftover stuff here, x dx. So x dx. And so you can integrate dv. You simply add 1 and divide by it. So x squared divided by 2. And now the derivative of ln of x is 1 over x dx. And so then this thing is going to be equal to what? You have x squared over 2 times ln of x quantity squared. That term stays. And then minus all this stuff that's going to follow. So you go down and integrate, subtract the integral across. So this is going to be an x squared over 2 times ln of x, and then minus the integral. So now when you multiply these together, the x's cancel, but that 2 is going to stay. So basically you just get an x over 2, because the 2 x's cancel, and then a dx. And so then this is going to equal, you have x squared over 2, ln of x quantity squared, minus, and I'm going to bring that minus sign through, so x squared over 2, ln of x. And then a minus makes this a plus, and then I can integrate this out. I can add 1 to it and divide by it. So this is going to be, basically, you have 1/2, and then you add 1, so x squared, and you divide by it. And then that's all we need plus c. And so now my final answer would be what? It would be x squared over 2 times ln of x, oops, that's a square, ln of x quantity squared, minus an x squared over 2 times an ln of x, and then plus a 1/2 x squared over, oh, I guess I should do x squared over 4, right? Let's do that, because I should put those 2's together. I was kind of busy looking at something else there. So this is actually 4. So let's just wipe that out. So divided by 4. Right, because 2 times 2 is 4, and then plus c. And you can actually, if you want, you can just leave your answer like this. I was looking at it, so I was like, oh, hey, they all have x squareds in common, and divided by 2's. You could probably factor those out if you really wanted to. But let's just leave it like this, because I think, you know, the hard stuff is really, or the new stuff is just learning how to use integration by parts. And this is a good example, because you don't do it once, you actually do it twice. All right, so let's look at the last example. This is the trig substitution example. And so on this one, the idea is you want to make a right triangle. So here's my right triangle. And so what I'm going to do is I have this x squared plus 9, so square root. So that's, it's plus, it goes on the hypotenuse. And then you can choose where you're going to put the x, and it's not just 9. Remember, it's 3 squared. So I usually like to put the x over here and the 3 here, but you can put it on either side. But make sure you put 3 and not 9. And so now the idea is you want to do this trig substitution. So you want to express all this x stuff in terms of trigonometric expressions involving theta. So first I want to get rid of this x somehow. So I'm going to use x and 3 because those are the two easy sides that involve x. And so that's the tan of theta. The tan, remember I'm using this idea of SOHCAHTOA. This is how we define sines and cosines and tans in terms of a right triangle. So the tan of theta is the opposite over the adjacent side to the angle. So the opposite side of the angle is x, and the adjacent is the one next to, so that's 3. And so then I can solve this for x. So I'll multiply both sides by 3 and get 3 tan theta is equal to x. So I have my x, so I can plug in there if I need to. I need my dx. So to find dx, you just take the derivative of both sides. So 3 times the derivative of tan theta is secant squared theta. And we like to write the d theta on the left. And the derivative of x is just 1 dx. And so now I have dx, and I already have my x. And so now I just need this last thing here, that square root of x squared plus 9. Well, that's this piece of the right triangle. And then I'll use this piece down here because it's the next easiest side. So that's the adjacent hypotenuse. So I know that the cosine of theta, that's the ka, would be 3 divided by the square root of x squared plus 9. I'll flip both sides and get a secant theta on the left is equal to the square root of x squared plus 9 divided by 3. And then I'll just multiply both sides by 3, so 3 secant theta is equal to the square root of x squared plus 9. And so now I can plug in for all of my pieces, basically. So this is going to equal the integral of 1 divided by, I have x squared, so here's my x, and it's equal to 3 tan theta. So I'm going to square that. That's going to be 3 tan theta, and that's squared. I have it times the square root business. That's right here. That's my 3 secant theta. So times, I'll write a 3 secant theta here. And on top I have dx. Now dx is my 3 secant squared theta d theta. So I'll write that right here. So 3 secant squared theta d theta. Now remember, the x stuff is still there. It's just on the other side. It's like you turn this over and there's that. If you turn this back over, you'll have the dx on the other side. Where the square root of x squared plus 9 go? It's still there. If you turn that over, it's on the other side. Where did the x go? Well, it's still there. It's right there. If you turn it over, it's on the other side. So you just made what's called a trig substitution. And so it doesn't look the same, but it still is the same. So let's clean this up then. So this is going to be a 1 divided by, and then you have 9 tan squared theta, because you're squaring out the 3 tan theta. Well, this 3 is going to cancel with that 3, and this secant theta is going to cancel with one of those. And so on top, you're going to be left with a secant theta and then a d theta. Now this one's kind of tricky because it's like, well, what do you do from here? You know, the derivative of tan theta is secant squared theta, but you don't have a secant squared theta, you just have secant theta. So if you ever get stuck like this, sometimes you can just convert to sines and cosines, and everything will take care of itself, basically. So let's do that so you can see what happens. So what we have here is 9, and then sine squared theta, tan squared theta is really a sine squared theta divided by a cosine squared theta. And then a secant theta is really a 1 over cosine theta. Now remember, when you divide by a fraction, you multiply by its reciprocal. So here, what you really have is you have cosine squared theta on top, divided by, you have a 9 on the bottom and a sine squared theta on the bottom, and then times this 1 over cosine of theta d theta. Now my brain's starting to see the idea. See, these are going to cancel, and you'll have a function on the bottom and its derivative on top. So this is going to be equal to the integral. One of these cosines of theta is going to cancel with one of those, so there'll be a 1 there. So you just get a cosine theta on top, and then you're going to get a 9 sine squared theta on the bottom, d theta. And in fact, if you really want to, just to clean it up a little bit more, we can just take that 9 and move it to the outside. So of course it's not 9, it's 1/9. So we move out a 1/9 to the outside. And it's real clear. There's a function sine of theta, and its derivative's on top. So I'm going to use substitution just to make this really clear, or if you like, you can guess and check. But it's sine of theta. The derivative of sine of theta is, of course, cosine of theta d theta. I see here where to plug in, so I'm going to plug it in right here. So it's going to be equal to 1/9 the integral. I have my u squared on the bottom, so I'm going to write 1 divided by u squared. And then on top here, this thing right here, remember, this is just your du. So then you have du. And I can rewrite that, because this is actually one of my types. It may not be clear, but I'm going to rewrite it as u to the -2 du. So it's just a power of u. So the idea is you're simply going to add 1. So I have 1/9. I'm going to add 1 to it. So u, -2 plus 1 is -1 divided by -1 plus c. And so this is going to be equal to -1/9 times 1 over u plus c. Now I can't leave it like that. I have to plug in for my u. So remember, your u is sine of theta. So this is equal to negative 1 over 9 times sine of theta plus c. And then sine of theta is something else altogether. So if you come back up here to your right triangle, we can write down what sine of theta is. So let me write it down. Let me write it down in red. So right here, we can use our right triangle, and I can write down the sine of theta. It's the opposite side over the hypotenuse. So it's x divided by the square root of x squared plus 9. And so I'm going to come down here, and I'm going to plug that in for sine of theta. So that's going to be equal to negative 1 divided by 9. And then what did I say? This is going to be x divided by then the square root of x squared plus 9. That was the sine of theta. All plus c. Remember, when you divide by a fraction, you multiply by its reciprocal. So we're going to flip this thing right here, and we just get the square root of x squared plus 9 on top, divided by a 9x on the bottom, and then all plus c. And that's my final answer.